We've covered it several times by now, but hopefully you remember that if you have a geometric series, that the geometric series converges only if that r there is less than 1. So that value that you're taking the powers of each time is less than 1. And I'm bringing that up because we're going to relate that to a power series. So we have a power series centered at C, and this is just a generic form. So what we want to talk about is some properties of this, because it's a series, so we naturally want to talk about convergence. So the convergence of this series happens one of exactly 3 ways. The first way is that it converges only if you plug in x equals c. And this is a pretty useless case, because what it means is if I plug in c, every term here disappears except in the case when n equals 0, because this will just be 1. So your function is just a constant function. It's not very helpful. It may be true, but it's not. It may be true, but it's not very helpful. So it diverges pretty much everywhere. The second one is the most useful one, which is that there's some r number that says, okay, if the distance x is from the center, so the distance x is from C, is within r, then it converges. So if you think about that, what it's saying is if there's some center C, then there's a distance you can go to the left and a distance you can go to the right called r, that as long as you're within that distance, it'll converge. So maybe the center was 2 and r was 5. So you could go all the way up to 7, but not exactly to 7. You could go all the way up to 7, so you could plug in like 6.5. Or you could go down and maybe subtract 3. You could go down to -1. Those values would work. But if you try to plug in 10 into the power series, it would diverge. So this can be useful, but it has limited usefulness because the series is kind of temperamental. It's okay here, and then it becomes unstable outside of a certain range. And then finally, this is the ideal case, that it converges absolutely for every x. And there are a lot of power series for which this is true, and we'll talk about some of them. And you'll notice I did these little r's here. R is what's called the radius of convergence. So, which makes sense, right? We talked about there being a center of 2, and you could go to the left or you could go to the right. And in that particular case, that's, think about that as a radius, how far you can go away from the center. Right? You have a circle with a center and a radius. Okay. But in the case where it converges only at the center point, that essentially has no radius because you're just right on the dot. You're not going anywhere. And then in this case, the radius is infinity, because no matter how big of a radius you draw, it's always you have to cover every possible condition, so your radius just grows without bound to infinity. And in this case, the radius is just r, which is not that useful to say, but usually we get a number like r is equal to 3 or something like that. And the set of all values for which it converges is called the interval of convergence. And that can be a little tricky, because if your radius is 3, but your center is 2, then your interval goes from -1 to +5, right? Because the center's here, so the radius comes out this way and it comes out that way. So just because your radius is 3, it doesn't mean your interval is -3 to 3. It's that interval shifted over by however much your center is, right? Just think of it like a circle. And you have a little peg for your center that you're moving. We'll do a quick example here. We want to find the radius of convergence for this power series. So you want to ask yourself, okay, for which x values can I plug in and this thing not blow up and actually give me a reasonable result? So what we can do is we say, okay, well, I know from the ratio test that if I can get the successive terms, if the ratio of the successive terms ends up being less than 1, I know it converges. And we're going to leverage that, because remember, that's pretty much related to it being a geometric series. So I do the n plus 1th term divided by the nth term, and I'm going to call that un, and that just is everything here. We'll call that un. So we plug in un plus 1, everything's n plus 1's here, and then we divide the nth case, and then you flip it, convert into multiplication, simple enough. Now I have n plus 1 4s and I have n 4s, so I have one more 4 here, so that stays on bottom. I have one more x here that stays on top, and I have one more negative 1, which also stays on top. Now, obviously this is an absolute value, so the negative just gets absorbed by the absolute value. And if we look at the limit, limit depends on n, but nothing here depends on n. So the result of our limit is x over 4, which isn't a number. But if you recall, the ratio test converges, or the ratio test tells you the series converges if and only if, well actually not if and only if, but only if this thing is less than 1. So, or rather, actually technically that's if. It's not an only if. I'm sorry, apologize. That's an if. So this limit converges if this is less than 1. So what I have to do is I say, okay, well, under what conditions is this less than 1? Well, obviously that's true if the magnitude of x is less than 4. So what that tells me, as long as the magnitude of x is less than 4, that means it could be up to positive 4 or back to negative 4. Well, that looks like a radius of 4. So generally speaking, when you get to this point, whatever it's less than, that'll be considered the radius of convergence.